Hi, everyone. I'm Chris Sommers from Keysight Technologies, and today we're going to learn about Table-Driven Interface, or TDI. Our speakers are Sayan and James, both from Intel. Sayan is a cloud software developer, and James is a cloud software architect. TDI provides both a local API and a remote gRPC-based runtime specification that is P4 architecture independent and usable for both P4 programmable and non-P4 fixed function management. I was fortunate to see an earlier talk about TDI in the P4 API working group, so I'm looking forward to this update. Take it away, gentlemen.
Hi, everyone. Table-driven interface usages and advantages. What is TDI? Table-driven interface is a target-agnostic interface which is being developed initially by Intel as part of our IPDK initiative. IPDK initiative is Infrastructure Programmable Development Kit. Recently, it was open sourced. So TDI has been open sourced as well. It's present under P4 Lang TDI. So the TDI provides a common C++ and C front end. It's there in P4 Lang, and this front end can be used by control plane applications to program underlying hardware. So the targets which can implement TDI could be anything. Initially, we are planning to integrate TDI with P4 DPDK, with Tofino family of switches, with IPUs by Intel, and with FPGA-based IPUs by Intel. Targets need to implement their own backend, which in this diagram you can see are the purple layers. The green layer is what is being open sourced in P4 Lang. So the idea is that every runtime entity is represented as one or multiple tables, whether P4 or non-P4. So match action tables, action profile, counters, selectors, everything is converted into entity called as table. And that is also true for any non-P4 component as well, like ports or traffic manager or multicast manager. So TDI is based on a JSON schema. We call it TDI.json. So it's a JSON-based contract between the front end and the control plane on how these tables look like. The idea is very similar to P4 info in P4 runtime, for people who are more familiar with P4 runtime. So the compiler, the P4 compiler generates TDI.json from the P4. And the target driver can also provide handwritten TDI.json files for different fixed features for like ports or multicast manager. So there is a TDI JSON parsing library which is present in P4 Lang, which is present in the open source repository. It parses all of the JSON files and it creates and it brings up TDI module. Okay, so going forward to how table structure is achieved, or what is the table structure. So in this diagram, a match action table is being converted to a TDI table. So let's say the match action table consists of certain key fields, certain actions, and a direct counter. So the corresponding TDI table will look like a group of key fields, a group of actions, and something called as common data. So essentially, this TDI table will allow users to program entries, and each entry consists of key and data. So key is simply these fields. Data consists of the action specific fields plus all the common data fields. An equivalency like struct and union construct can also be imagined here. The reason this C structure, I'm bringing up this C-like structure, is to demonstrate that how a non-P4 like feature can also be translated into a TDI table. For example, for ports, the key fields can be like one key field, which is port ID, and you can have data fields, which will be attributes of the port. So TDI JSON table structure to API mapping. Let's consider the same table which we had earlier, the match action table. So this table, you can go and use these APIs to program entries in this table. So let's say the user programs 3 entries, and each entry will have a key and a data. The key consists of 3 different fields. The first is an exact match field. The second one is a ternary field. And the third one is a compiler generated field for match action tables, where it generates this field for ternary fields. So this field, even though it was not provided by the user in the P4 program, this was generated by the compiler. And the data, it consists of action spec and common data. So in this example, you will notice that entry 2 and entry 3 might have a clash if the packet consists dest adder as this, and the source adder as exactly 6.6. Then the lower match priority will get a higher priority and entry 3 will hit. But let's say if a packet comes in with 445555, then entry 2 will get hit. Default entries can also be present in tables. So the table-wide APIs which we support are table clear, attribute set, operations execute. Attributes are table-wide properties. For example, there is and these attributes and operations are all target specific. So targets can choose to implement whatever kind of attributes or operations they want for a table. This is an example for match action table, where we have an operation called countersync, with which you can sync all the hardware counters. So moving on, API types, simple. So the different kinds of APIs which are available are infrastructure APIs, which have device management APIs, like adding devices, removing devices. So let's say if someone wants to develop a gRPC server, they can use these device management APIs to manage set forwarding pipeline kind of construct. Session APIs, these APIs provide batching and transaction semantics. Then table APIs. Table APIs are the APIs which we talked about just earlier. So simple API workflow looks like there is a device manager. You can get a device from a device manager. Then there is a mapping of programs to TDI info. So TDI info is an object which contains table representations of all the TDI tables present in that pipeline. You can get to a table representation. Once you get to a table representation, you can allocate keys, allocate data objects. Then on the key object, you can set value on all of the fields using their field IDs. You can do the same thing for the data object. You can set values on the field, on all of the fields. And then finally, when your key and data object are now all set valued and baked, and the information is baked into them, finally, a table entry add can be called with target object, session object, key and data object. So key and data comprises the entry. Session can be used for achieving parallelism, or to indicate that, let's say, this entry add was part of a batch. This target object is again an object using which different targets, let's say DPDK or a switch, they have the flexibility to create smaller components, smaller sub devices of a device. Let's say if a certain IPU or switch wants to support something like pipe IDs, or something like programming all of the pipes at once, then this target object allows them to do so. Moving on, TDI front ends. So TDI exposes two different front ends, C++ and C. And then there is a Python CLI, which uses the C front end. Then internally, the TDI, so talking about internals, TDI interface is one common C++ top level interface. This is architecture agnostic and target agnostic. The top level C++ interface, the C front end, and the CLI. By architecture, I mean P4 architecture. Architecture specific code can be written inside this TDI repository. This provision is being provided only so that different targets, if they want, they can make use of any common code. This is not required to be used, or like, for example, if someone wants to come up with their own P4 architecture, they can choose to keep it in their own repository. If someone doesn't want to adhere to a P4 architecture, they can just, for example, port tables, they can just directly inherit from the top level interface. So this diagram over here, it's showing the C++ inheritance. And as you can see, it provides flexibility in all different ways. Moving on, advantages of TDI. Control plane code uniformity, since the front end is target and P4 architecture agnostic. Control plane applications can be written which are uniform across different targets as well. Many control plane applications are written which do something very specific for a specific target. So of course, those applications won't be specific, but let's say if someone wants to develop a generic application like a gRPC server or a CLI, or let's say a cache storage application which goes over all the tables in a target and reads all the entries and stores in a database, then writing such an application is very simple. You just loop over all the tables, loop over all the entries, and write them in your database. And the same small code will work for any kind of target which supports TDI. Second advantage, target vendor, ease of feature addition. So any new feature, whether new P4 extern or non-P4 feature, it's relatively easy to add. Targets just need to implement backend, and all the front ends and CLI and everything else will just automatically work. No new messaging protocol or no new extra changes need to be made in any of the generic applications, at least. Third point, similar to second only, no extensions needed for new features in the front ends and the TDI tools themselves. TDI versus P4 runtime. So TDI is primarily native APIs in C++ and C. P4 runtime is primarily gRPC and protobuf based. So for TDI runtime, we are still under discussion whether we want to move towards TDI runtime, a new gRPC and protobuf based specification, or we want to keep using P4 runtime, or even we are open to designing P4 runtime version 2.0 probably, which will be more friendly with TDI. Currently, the plan is, at least in IPDK, that we will be using P4 runtime as the gRPC interface everywhere. Underneath it will be all TDI. So second difference is TDI APIs are all based on an abstract structure called a table. In P4 runtime, the API flow to program different entities are all different because follows a messaging structure. So there is a separate message for meters, match action tables. Third point, TDI provides an interface which is P4 architecture agnostic. It's not tied to PNA or PSA or any P4 architecture. It can potentially be used for non-networking APIs as well, like compute or storage. P4 runtime, on the other hand, is tightly knit with PSA. TDI is extern independent. So any new extern, let's say, if added to any P4 architecture, it doesn't require any front-end changes. It will require making enhancements to the P4 compiler so that new TDI table in the JSON itself would be exposed. Targets will need to implement their backend, but front-end changes will be none. In P4 runtime, however, in addition to the compiler generating new P4 info and new backend support, front end also needs changes. So P4 runtime allows extensions to be programmed via externs, but this is again very vendor dependent. It doesn't have a generic specification guideline. So the example below over here shows an example taken from the P4 runtime specification where adding an extern support for, let's say, a new counter, it requires a P4 runtime message in addition to a P4 info message. This introduces compile time dependencies and also vendor-specific control plane application code. In TDI, however, yes, a new TDI info table structure will be formed, but since the table schema is following the same table schema of TDI JSON, it fits in seamlessly with the front end, and so no new P4 runtime message is required. The same API works. That's all from my side. I'll let my co-speaker James take over from here. He will be speaking more about P4 DPDK integration with TDI.
Thanks, Sayan. Okay. Yeah, I'll be talking about the P4 DPK target. The P4 DPK target is the first implementation of TDI. And this is a P4 Lang project that is available in P4 Lang. And currently the upstreaming of the TDI implementation is in progress, and it contains both the BFRT interface as well as TDI interface. BFRT is the predecessor to TDI, and both the code exists right now. And to explain more about the P4 DPK pipeline, P4 DPK is a DPK-based software pipeline that is configurable through P4, and it supports the PNA and PSA architectures, and P4C compiler with the DPDK backend generates all the necessary runtime files. And so Sayan discussed front end includes the TDI C++ class and the C wrapper and the TDI JSON parser that conforms to the TDI JSON schema. And there's also a TDI CLI that the front end provides. And DPDK target backend supports those interfaces. So there are TDI C++ backend code for P4 tables and non-P4 tables. Currently, we support port and vport related functions through TDI. And there are resource managers that interface with the low-level driver code that we have that understands the interface to the target driver. So in our case, P4 DPDK provides certain API, and low-level driver understands what that API is, and it can do the mapping to the API. The DPDK target also repo contains the BF switch sample application, and more details can be found in the README of the P4 DPK target repo. Okay, so how does DPDK target implement TDI? Sayan has shown this similar picture earlier. We're double clicking a little further in detail. So the front end is provided through the submoduling of TDI, and the TDI backend implementation consists of a set of C++ class implementation that implements different table types. So there are P4 tables, and there are port-related tables, and we're adding on more types of tables in this layer. And underneath that layer is a resource manager layer, which does the mapping from the TDI onto the backend target configuration. And there's a LD layer, as mentioned before, that does the provides access to the target API. And the artifacts for P4 functionalities, artifacts that the P4 compiler generate are P4 info, TDI JSON, context JSON, and DPDK pipeline spec file, which is the binary that goes into the pipeline itself. And the P4 info will be used by the control plane, which is in the upper yellow section over here. And the control plane will also consume the TDI JSON, so that the P4 info to TDI JSON mapping can be done in the control plane. And TDI JSON would be consumed by the parser in the front end as well to understand the user interface. And the context JSON is something that is consumed by the backend layer as well as the resource manager layer. And the context JSON is something unique that we do that provides help for the driver code that sits here to implement mapping of the TDI interface to the backend interface. So a lot of things that would have been hard-coded in the driver code is actually done through the help of context.json, and a lot of these are driven from the compiler. For the non-P4 tables, there are handwritten files, JSON files that define the attributes of these functionalities, and they're consumed by the control plane as well as TDI frontend. And there's no use of context.json for these fixed functionalities. Before we discuss more on these classes, I want to highlight some TDI infrastructure objects. And so there are infrastructure objects like a device, and device is pipeline target. And there is also something called program config in the TDI that really corresponds to a P4 program. So for each program config construct, there's a P4 program and the accompanying TDI JSON files. So that's what a P4 config is. And there is a P4 pipeline, which is the mapping of P4 program onto a target. So with each P4 pipeline, there is a target pipeline binary that goes with it, as well as the context JSON file that goes with the P4 pipeline. And there's a concept of P4 pipe scope, which is a grouping of target pipelines in a device. So the TDI provides certain capability to support these infrastructure objects, and P4 dpk target provides a subset of what TDI provides. So for device, multiple devices can be supported through TDI library. Currently, only a single device can be supported per TDI library for P4 dpk target. And for TDS can support multiple programs, P4 programs per device, and dpk target can support up to 4 P4 programs per device. And TDS supports multiple P4 pipelines per P4 program, whereas DPDK can support a single P4 pipeline per P4 program. And TDS supports multiple logical pipes per P4 pipeline, whereas P4DBK provides a single logical pipe per P4 pipeline. On the right-hand side, it's showing the configuration file that is used to initialize the PF switchd application. And this the configuration file shows the similar hierarchy of these constructs that we just talked about. So talking a little bit about how P4 and P4 runtime is supported, I'd like to first talk about some characteristics of the P4 functions. So these P4 related functions are typically, they are programmable through P4, and TDI JSON files are compiler generated, and the context JSON is used to mapping to target pipeline. P4 function resources are allocated by compiler at the P4 pipeline level, not at the device level, and they're managed by the driver at the P4 pipeline level. And the P4 function JSON files can be loaded at the TDI, the library initialization time, but also at the runtime through set forwarding pipeline config. So if we look at the P4 runtime messages for each of these major messages, there's a corresponding TDI JSON table types that the compiler generates. And so there's for giving something like a table entry with the action, direct action, there's a table type called match action direct. And there is also then in the P4DBK target repo, there's C++ backend classes that handle these type, each of the table types. So there's a match action direct class that consumes information on the match action direct table type and takes the implements the appropriate things in the code. So there are these set of runtime messages. I'm showing a subset, and the compiler generates these table types, and then these C++ backend code process these table types. Now, our P4DBK target has been integrated with the ONF Stratum P4 runtime server, and this has been done as part of IPDK, Intel IPDK integration. And there is actually a IPDK container that pulls in TDI and Stratum P4 runtime, as well as the P4DBK target and DPDK target itself that the one can build, and it serves as a really good tutorial material, and it's a hands-on material. So I highly encourage anybody who's interested to go ahead and build a container, and they can see all these in action. And talking a little bit further on the fixed functions, so to contrast with the P4 function characteristics, these fixed functions are not programmable with P4. TDI fixed function JSON files are handwritten at this point for P4DBK target, and there's no context JSON that is used. And all the fixed function resources are managed at the device level, and they are shared by all P4 pipelines. So if you configure a port, then that port is visible to all the P4 pipelines, and the management of the port is not divided into at the P4 pipeline level, but it's managed at the device level. And the fixed function JSON files are loaded only at the TDI library initialization time. So it cannot be loaded at the runtime. And again, the ONF Stratum NMI server is integrated with the P4DBK target. And this has been done as part of Intel IPDK integration. So the more information can be found in the Intel IPDK.io website. And currently, I mentioned before, port and vport are being worked on, but more functions are currently being worked on to be added. Okay, so finally, talking a bit about the roadmap. TDI specification document version 1.0 is currently being worked on, and we expect to have it by July of this year. And also, integration of the TDI with the P4DBK currently is being worked on and being upstream, and we hope to have that version out by July of this year as well. And there is currently effort for TDI workgroup to be integrated with the P4Lang, and we hope that tentatively hope that would be done by July as well. So, yeah, that's that's the what we have.
Well, thanks a lot, guys. That was a real interesting presentation. It was really clear, and I think it's really timely. I liked also the sneak preview about P4 DPDK. You've really whet my appetite, and I look forward to seeing the other talks on that subject at the workshop this year. I hope I get a chance to play with it in my spare time. As you mentioned, TDI is essentially an open version of Barefoot Runtime, which has been used by a lot of Tofino software developers, including myself. I've done a lot of work using Tofino. And I think it's great that Intel's taken all that IP and is opening it up and sharing it. But as a developer, it kind of leads me to a few questions. I'm wondering, will TDI become the de facto API for Tofino, software development environment? And is BFRT being ultimately deprecated?
That's a good question. BFRT will eventually be deprecated slowly over time. But since we have a number of users, both internally and externally, we will be doing it over phases. We plan on developing internal translation shim layers so that users can still use the BFRT APIs. And internally, if we will provide like compile time options so that they can run TDI backend with it. So with the BFRT front end, TDI backend will be, they will be able to use that. So the first step of deprecation will be deprecating the BFRT backend.
I see. Well, that sounds like a good way to ease the process. Would there be some way to sort of automatically or semi-automatically change people's existing code to use TDI natively if they wanted to bite the bullet?
We don't have a plan for giving out such a script or a tool yet, but it is a good idea. If we do roll out some search and replace kind of tool, it will, of course, come with a disclaimer that it is not foolproof or not exhaustive, and users will still need some kind of manual diligence after that.
The semantics are pretty close though, aren't they? So it'd be pretty easy to translate, I would hope.
Semantics are pretty close. We have changed a few C-like structures into more C++ object inheritance model so that it is easy for different targets to implement target specific details.
Sure. You didn't want to be constrained by original ideas. You really used all the learnings and the forward-looking ideas to make it a little better. That's good. Do you see TDI being useful for targets like FPGAs or maybe a BPF backend, that type of thing? Have you ever considered that?
I'll let James take that question, probably.
Yeah, so definitely I think we see the TDI to be useful for those type of targets as well. And it's not even just for P4, right? So it's for really a whole variety of functionalities that the TDI can support. So I think the, even currently the P4 TDI are being generated by the compiler, and even for the fixed functions. And I think we can foresee that the TDI JSON being generated by some sort of tools. So some sort of a Yang, open config Yang model conversion to TDI JSON file, so that the semantics being sent over the RPC API is exactly the same as the semantics that is in the local TDI API. So I think that kind of development, I think we could foresee. And also TDI is used as a sort of target agnostic standard interface for Intel IPDK effort. And there's a lot of code being developed for control plane that for IPDK recipes for storage and for Kubernetes and networking. So all those will use TDI API. So there's an effort to develop a lot of Intel products, such as Intel ES3000. And there's a FPGA-based IPU the Oak Spring Canyon that is being developed to conform to as the backend of TDI. So certainly, I think we foresee a lot of drivers that will be the backend of the TDI going forward.
Oh, great, great. Golang is becoming pretty popular, and a lot of people are using it more and more in SDN type applications. Have you ever considered providing an idiomatic Golang API for TDI?
I can take that. So currently on only C and C++ are the present front ends natively. There is no current plan for Golang or Rust as native API, but we will definitely be open to future developments in those languages. For Golang users today, P4 runtime is the only recommended way. So they can create Golang clients to work with P4 runtime, and P4 runtime. We will be providing the P4 runtime to TDI adapter in Stratum, so that can be used by Golang clients.
That sounds like a fun hackathon idea. Do you hope other silicon vendors will adopt TDI? For their ASIC or their SDKs?
Yeah, we hope so. We want other vendors to adopt this. We are planning on integrating a working group with p4.org soon. That is just that we, with all the work that is going on inside Intel, things are taking shape and changing very fast. So we are planning to get it done, hopefully with our July release, somewhere around that time when we will be coming out with the specification. Since the same set of people who are in the P4 API working group, they would be mostly the same set of people who will be interested in TDI as well. I think it more than justifies integrating TDI working group as part of that.
Great. Well, thanks for answering my questions, and thanks for the great presentation. I think it's pretty exciting. It's a great milestone to have this opened out and have specs coming forth, etc. So good job, and I look forward to seeing people start using it more. Thanks a lot. And thanks for the talk, everybody.
Thank you.